Hey there and welcome. Today, we're going to tackle a topic that, let's be honest, can make even seasoned calc students sweat a little: double integrals over circular regions. But what if I told you there's a way to turn a nightmare of a problem into something surprisingly elegant? So yeah, let's unlock this thing.
You know the feeling, right? You're just staring at this integral, and it's got these terrifying square roots and the limits of integration. You just know it's going to be a long, messy fight. And you're thinking, man, there's got to be a better way. Well, guess what? There absolutely is. I mean, just look at this. On the left, you've got your typical rectangular coordinate setup. And yeah, those square root limits are just awful. And then on the right, that's the same exact problem in polar coordinates. The limits are clean, they're constant. It is a total game changer. So who's the hero of our story today? It's polar coordinates, of course. The whole idea here is that we stop thinking in terms of left-right, up-down, x and y, and we start thinking in terms of a radius and an angle, r and theta. And that simple shift in perspective, that's what unlocks everything. Okay, so how do we actually do this? It all starts with two really fundamental relationships. Anywhere you see an x, you're going to swap it out for r cos theta. And anywhere you see a y, that becomes r sine theta. This is pretty much step one for transforming our whole integral. But wait, it's not quite as simple as just swapping out x and y. There's a secret weapon in this whole conversion, like a small but absolutely crucial piece that makes the entire thing work. And trust me, if you forget it, the whole method just falls apart. All right, so we've swapped out our function f of xy with its shiny new polar version. Awesome. But what about that dA at the end? You know, that little area element? In rectangular coordinates, that's just dx dy, no big deal. But what does it become in polar? It's not quite as simple as just dr d theta. And this is it. This is the secret weapon. That area element, dA, it becomes r dr d theta. You absolutely positively have to remember to multiply by that extra r. I'm not kidding, this is the most common mistake students make, and it's also the absolute key that makes this whole thing mathematically solid. Okay, enough with the theory, right? Let's see this superpower in action. We're going to dive into a first example, one that would be a real pain to do with rectangular coordinates. So here's the problem. We need to find the volume under this surface, this z equals 9 minus x squared minus y squared, which is a shape called a paraboloid. Now pay attention to this part. If we want to find the base of this shape on the xy plane, we set z to 0, right? And what do we get? X squared plus y squared equals 9. Hey, that's a circle with a radius of 3. A light bulb should be going off right now. This is a perfect candidate for polar coordinates. And just watch how beautifully this all falls into place. So our radius, r, is going to go from the center out to the edge, so that's 0 to 3. Our angle, theta, needs to go all the way around the circle, so that's 0 to 2 pi. And our function, well, 9 minus x squared plus y squared just becomes 9 minus r squared. So simple. Now we just put all the pieces together for our integral, and what's the one thing we can't forget? Our secret weapon, that extra r. From here, we just do the integration, and honestly, it's a super straightforward calc problem now. And what do we get? Our final volume is 81 pi over 2. Just look at that, a clean, beautiful answer to what could have been a really messy problem. Okay, that was cool. Let's try another one. Build on that. A slightly different scenario. What if the area we're integrating over isn't a solid disk, but like a ring? A donut shape? The technical term is an annulus, by the way. So for this one, we're asked to integrate this function, cos of x squared plus y squared, over the specific region. It's basically a slice of that ring shape, right? It's between a circle of radius 1 and a circle of radius 2. And it's only in the first quadrant. I mean, come on, a description like that is just screaming at you to use polar coordinates. And the setup? Just as easy as before. Okay, first quadrant means our angle, theta, goes from 0 up to pi over 2. And between the circles means our radius, r, goes from 1 to 2. The function, cos x squared plus y squared, becomes cos r squared. And look at this! When we set up the integral, we get cos r squared times r dr. That extra r is exactly what we need to solve this thing with a simple u substitution where u equals r squared. It's almost like the problem was designed to be solved this way. It's perfect. So we do the integration and bam, we get this result. And once again, we took a problem that looked pretty intimidating at first, and just by changing our perspective, we made it totally doable. All right, You ready for the grand finale? Because now we're going to use our polar coordinate superpower to solve one of the most famous and most important impossible integrals in all of mathematics. This is like the ultimate proof of how powerful this technique really is. This right here, this is the Gaussian integral. That function, e to the negative x squared, is the heart of the normal distribution. You know, the famous bell curve you see everywhere in statistics. But here's the thing. That function has no elementary antiderivative. What does that mean? It means you can't just integrate it using the normal techniques you learned in first semester calculus. It seems impossible to solve. So, how do you solve the impossible? Well, with a move that is pure mathematical genius. The trick is, you take the integral, let's just call it I for short, and you square it. Now, by using a different variable in the second copy, say y instead of x, we can actually combine them into one single double integral that covers the entire xy plane. It's a wild move. And here comes the magic. By squaring it, that integrand becomes e to the power of negative x squared plus y squared. And what does x squared plus y squared become in polar? It's just r squared. So our function is a simple e negative r squared. And our new polar integral has that beautiful rdr term, which means it's now perfectly solvable with another u substitution. So we do the math, and we find that I squared, the square of our original integral, is just pi. Simply pi. So think about it. If I squared is equal to pi, then the value of our original impossible integral has to be the square root of pi. I mean, how cool is that? It's a beautiful, profound, and totally unexpected result, and it was all made possible just by switching to polar coordinates. You know, this shows us something that's so much more than just a clever math trick. It's a really powerful lesson in problem solving. Sometimes the best way to solve a tough problem isn't to just keep banging your head against the wall. It's to step back, change your perspective, and see if there's a different way to look at it. Sometimes when you do that, all that complexity just melts away. Thanks for tuning in.